Taking a look at our practice question set. Practice questions on page 259, number 2 and 3. Number 2 says an automotive manufacturers test the handling ability of new car design by driving a prototype on a test track in a large circle at ever increasing speeds until the car begins to skid, I should say. A prototype car is tested and found to skid at a speed of 95 kilometers per hour. What's the coefficient of static friction here? Kilometers per hour, we want to circle that, draw attention to that because ultimately we want to convert that to meters per second, right? Do you guys remember how to convert to meters per second from kilometers per hour? Yeah, of course we do, right? We got to convert kilometers to meters by multiplying by 1,000, and then we convert hours to seconds, divide by 3,600. Let's write down some givens here. The radius of this circle is 100 meters. We know the mass of this car is 1,200 kilograms, although I think we're going to find that the mass of the car doesn't matter. Remember we saw in the example question on Wednesday that the mass ends up canceling out. I think we're going to find the same thing here. The speed is 95.0 kilometers per hour, which we're going to convert that to meters per second by multiplying by 1,000, dividing by 3,600. What does that work out to be? I want to say it's something like 26 or something like that. I don't know exactly. What is the exact number? Ben, you have that? 26.38, thank you. And we want to find the coefficient of friction here. Just like that question that we did on Wednesday, we say the centripetal force, well, it's equal to mv squared over r, but we know that the centripetal force is caused by something. In the case of the Earth going around the sun, it's not quite a circle you're going to learn later on this unit, but more or less a circle, that centripetal force is caused by what? The Earth goes around the sun's centripetal force. What's it caused by? What keeps the Earth in orbit around the sun? Gravity. Right? So the centripetal force would be caused by gravity, or the centripetal force could be equal to gravity. In the case of the electron going around the nucleus of an atom, the centripetal force is caused by an electric force. So we could set those two equal to each other. In the case of a car going around a turn, the centripetal force is caused by friction. So we can set those two equal to each other. Now, understand that we don't always have information about friction. We can still, if we have enough givens, solve this problem just as F is equal to mv squared over r. We're not saying that every time you see a circular motion problem that you have to set the centripetal force equal to another force. We're just saying that you're allowed to. If you need to, if it's helpful to, then you can set those two forces equal to each other. All right, mv squared over r equals mu times the normal force, which assuming it's a horizontal surface, the normal force will be m times g. Mass does in fact cancel, and now we're looking for mu, the coefficient of friction. So the g is going down by dividing. Mu is equal to v squared over r times g. Let's sub our numbers into this. V is, we said 26.38 meters per second. Don't forget to square that. R is 100 meters, and G is 9.81. When you do the math there, we should get 0.710. Does that seem like a reasonable number? Go ahead. Yep. Yeah, that's exactly the same thing. So let's just clarify that. Ben said v squared divided by r divided by g. So I know exactly where Ben's coming from on that, right? He said, well, I got to take the g over by dividing, right? I'm going to divide v squared over r by g, right? That's correct. I've just simplified it and said v squared over r times g. It means exactly the same thing. Now let me justify that for you. G is the same as g over 1. Do you agree with that? Yeah. Okay, it's just the same as 10 is the same as 10 over 1. Or x is the same as x over 1. So if we want to simplify this a little bit, then we could say mu is equal to v squared over r. How do you divide by a fraction g over 1? Anybody remember how to divide by a fraction? Yeah, multiply by the reciprocal, which is 1 over g, which means that's the same thing as v squared over r times g. Does that make sense? Yeah. So I just tidied it up a little bit. from what you had v squared over r over g. I said v squared over rg. It's exactly the same thing, just a tidied up form of it, that's all. You don't need to tidy it up like I did. Like you leave it like this, that is absolutely fine. Okay? And it's going to work for you every time. All right? Does that seem like a reasonable number? Yeah, like coefficient of friction is usually between 0 and 1. Not always, we can get above 1, right? But usually it's somewhere in that 0 to 1 range. And if you remember some of the questions that we've done earlier on in our last unit, friction between tires and road, 0.7, 0.8, something like that. Okay, it seems reasonable. All right, number 3. 3 says a 600-gram toy-controlled car, or toy radio-controlled car, can make a turn at a speed of 3 meters per second on the kitchen floor, where the coefficient of friction is 0.9. What's the radius of the turn? We should convert grams to kilograms, although I think, once again, the units are going to end up, or the mass is going to end up canceling out anyways. Fc is mv squared over r equals mu times the normal force, but on a horizontal surface with no other forces acting, it'll be, the normal force will be m times g. Mass does, in fact, cancel. We're looking for r here. This is a little bit harder to rearrange for. R is on the bottom. What are you going to do first? Get it to the top, multiply by r. So we're going to say v squared is equal to mu times g times r. Solving for r, how do you get rid of the mu and the g? Divide them, yep. Take them down one at a time. You can. Or you can take them down both at the same time. We can say r is equal to v squared over mu times g. V is 3 meters per second. Square that. Mu is 0.90 times 9.81. So v squared over mu times g, we do the math there and we should get 1.0 meters. Now Ben, if you had have taken them over one at a time there, which you could have done, right? Would have been fine. Then this is what would have happened. Right? V squared is equal to mu gr. We would have got v squared over mu equals gr. And then the way you were looking at it before, we would have taken the g over by dividing, and we would have got v squared over mu over g equals r. Okay, because you took them both over at the same time like I did? Yeah. But you understand that it doesn't matter. You can take them over one at a time. We could have even said v squared over g divided by mu. It would have been the exact same thing. As odd as that looks to be the same thing, it is the same thing. I'm going to spend just a couple minutes today talking about another kind of force, and we'll use that term loosely, but explain what I mean by that in a second. It's called centrifugal force. We did address this one day, but we didn't talk about it in too much detail. The centrifugal force, as opposed to the centripetal force, is the outward force acting on an object moving in a circle. When you guys are in the gravitron ride at the Stampede and you're spinning around inside that circular room, you experience that centrifugal force being pushed out towards the wall. I was at Disney World here just a month or so ago, and I went on this ride. It's called Mission Space. Anybody ever been on that at Epcot? Epcot Center, it's called Mission Space, and it simulates this mission to Mars. And it's pretty neat the way they do it. You get in this compartment, and then it takes off, and you feel this intense gravity as you're taking off. How do they do that intense gravity? Well, you don't see what they're doing, but the reality is they're actually spinning you around. So you experience that centrifugal force towards the back of your seat as you're being spun around. Because you can't see the outside, though, you don't perceive visually being spun around. You just perceive the centrifugal force, which simulates gravity. And then they actually simulate no gravity by stopping it really quick. Now, you don't actually have no gravity there, but your body gets the sensation of no gravity. If you all of a sudden were spinning around really, really quick and experiencing that intense gravity, and then they stop it, and you're only actually experiencing real gravity, it makes you feel like you're experiencing nothing, right? It makes you feel like you're weightless for a short time. This centrifugal force is that outward force acting on an object moving in a circle. You've experienced it in your car. You go on a turn quick and you feel like you're being pushed to the outer door of your car. Yeah? Yeah, I'll explain that in a second here, okay? What I really should have put, okay, Demi asked why centrifugal is in quotation marks. What I really should have done is not put centrifugal in quotation marks, but rather force in quotation marks. Because the reality is, this isn't really a force. It doesn't exist. There is no such thing as centrifugal force. There's no such thing as a force pushing you outward. There is a centripetal force pulling you inward. That's, as I'm going around in that circle that I don't see, but still going around that circle in Mission Space at Disney World, then I'm being pushed inward by that outer wall. There is a centripetal force pushing me inward toward the center of the circle. But whenever we have an acceleration, which I do in that case, an inward acceleration, centripetal acceleration, I perceive a fake force or a pseudo force in the opposite direction. We went through this the other day, right? If I'm sitting at a stop sign, I get hit from behind, I feel like I'm being pushed back against my seat, but I'm not. It's really me accelerating forward that makes me feel like I experience a force backwards. When you're on that airplane and you're taxiing out, you turn the corner and all of a sudden you gun it from like 30 kilometers per hour to like 300 kilometers per hour. You know that feeling, right? When you've been on a plane and you go on the runway, it's like this massive acceleration. You feel like you're really being pinned back against your seat. Like you're being pushed back against your seat, but you're not. It's your seat pushing you forward, right? Whenever we experience an acceleration in one direction, we perceive a pseudo force or a fake force in the opposite direction. That's exactly what's going on here. The true reality of it is, Ben, I'll answer questions in a second, okay? When something experiences an acceleration, there is always a pseudo force Pseudo means not real, right? Pseudo means not real or fake force. In the opposite direction. So in this case, as an object moves in a circle, there is a centripetal acceleration, which is an inward acceleration. What are we going to perceive? We're going to perceive this fake force pushing outward. So you can maybe understand how we're going around in that circle, we feel like we're being pinned against that wall. Really, we're not being pinned against the wall. Really, it's the wall trying to push me toward the center. But how exactly, like, you've all experienced this too, probably, right? You've been on something, on some kind of ride, moving in some kind of circle, whatever, and you actually move to the outside, right? You actually move to the outside. When I was a kid at my elementary school, we used to have, once every 2 weeks, 1 week every two, because we split the playground and swapped off every 2 weeks. So one side, the good side of the playground, had a merry-go-round. And the merry-go-round, you don't see those very often anymore because, I don't know, people get hurt. People are a little soft. Yeah, I'll show you a video a little bit later on of maybe why we don't actually have merry-go-rounds, but anymore. But we used to have merry-go-rounds, and everybody always used to want to go on this merry-go-round. And I remember the merry-go-round had, like 4 spokes. This was the middle of it, and this was the axis of rotation. We're looking at it from above here now. And then there was this rail here, we'll call rail 1, rail here, we'll call rail 2, this rail here, we'll call rail 3, and this rail here, we'll call rail 4. And for whatever reason, I remember this here, there was a little nick in this rail, and nobody wanted that rail. Nobody would ever want to be on that rail because, for whatever reason, because of that nick on the rail. Because it was damaged goods, whatever. Sometimes you'd be on this merry-go-round, like let's say right here, and this thing would be spinning around pretty fast. You get 4 people holding on here, 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 and here, running around really, really fast, spinning this thing around like crazy really, really fast. And it was all you could do sometimes to hold on. Sometimes you couldn't hold on. Sometimes you would fly off, go outward, fly off. Or at the very least, you would be pushed out to the outside. That's not the wall pushing you in, because there is no wall there, right? Yeah, okay. Yep. So how do we explain that? How do we explain you physically being pushed out there? Or we physically, I shouldn't say physically being pushed out, physically going out. Somebody answered this question here the other day, and Ben, was it? Yeah, it was Ben, I think. Yeah. Do you know the answer now? Yeah, that's exactly what it is. It's Newton's first law. As I'm on this merry-go-round in this particular spot, I want to go in a straight line. But as it goes around in a circle, my straight line ends up taking me to, well, eventually I go to the outside. Now, I perceive that as being pushed to the outside because, look, if I'm at position 3 right now, I'm going in a straight line like this, but by the time I get to the outside, what's caught up with me? This position right here. So it feels to me like I'm being pushed to the outside. I'm going to show you a short little video to help you to understand that a little bit better. This is the perfect illustration of what's going on here, okay? This ball is in this cart. This cart is going to turn and go in a circle. This ball is going to go off in a straight line by Newton's first law, as Ben explained here the other day. Now, the perception of this ball, or if it was a person replacing this ball, would be that you were being pushed to the outside. And let me show you exactly how that happens here, okay? Let me press play on this. Watch the ball. It goes off in a straight line. Watch the cart. It goes in a turn. But look at the ball. Like, look at ultimately what's happening to it. The ball goes to the outside, right? But it's going to the outside, not because it's pushed to the outside. It's going to the outside because it's going in a straight line. And when it goes in a straight line and the cart turns, it has to end up going to the outside. But again, not because it's pushed to the outside. Now, if that was you, you would perceive yourself being pushed to the outside. But you're not really being pushed to the outside. It's really just going in a straight line. So this centrifugal force, this non-existent fake force, this pseudo force, is really just what? It's Newton's first law combined with, in some cases, the force of the wall pushing you in, right? Okay, not in this case, but in some cases it's combined with the force of the wall pushing you in, tricking you into thinking that you're being pushed out. Whenever we have an acceleration inward, we have a fake acceleration or fake force outward. Yeah, you had a question, Ben? Sorry.
Yeah, so you said on that ride around, like the room is turning, so you're going backwards.
Yeah.
And then when we drive and we turn, we feel like we're going to the side. Is it sort of like an optical thing?
No. That's a good question though. Here, let me bring this back here. So the ride that I was in, I don't know what it looked like what the whole scenario looked like. If you've ever been to Disneyland or Disney World, they do an amazing job at disguising things, right? Things seem so real. Like even as far as lineups go, you walk up and you think, oh, the lineup's not very big, and then you realize as you snake around, like you're, oh, there's the end of it right up there, and you turn, oh, no, it's going to be another hour, or whatever. They do such an amazing job of hiding things. So I can't see what's going on there, but let's say that it looked like this, okay? This is from above, this is my little capsule. There was 3 seats in each capsule, by the way. So I get in this capsule, my 2 sons get in this capsule as well. Then there's another capsule over here, and then there's another one up here, and so on and so on. I don't know how many of them there is, okay? But let's say that all 4 of these, or however many there are all attached like this, and this thing will spin around like this. Okay? Looking at it from above, okay, I'm sitting in this with my back against this wall. So here's my son, here's my other son, with our backs, literally with our backs against the wall. As we spin around with our backs against the wall, our backs we feel like we're being pushed out like this, right? And we feel that intense pressure against our backs. Really, it's the wall pushing me into the center, but it makes me feel like I'm being pushed out, right? Now, when you go around the turn in your car, you don't have your back against the outer wall, right? Your shoulder is against the outer wall. So what does it feel like for you? Well, as you go around the turn, it's like, like your shoulder, your body is being pushed sideways out. Does that make sense? Yeah. It's the same phenomenon. It's just the orientation at which you're sitting. That's all. Now, back to this ride again for a second. Like if you spin that fast enough, you could simulate half a G, like 4.9 meters per second squared, or 1 G, 9.81 meters per second squared. You can spin it around. It's like a centrifuge, just like NASA uses. Okay, you can simulate whatever gravity you want. I don't know what gravity they simulate. It would be bigger than 9.81 because they need you to feel like you're being pushed backwards. Okay, if they only have say 0.6 Gs, well, you're still going to feel that actual downward force of gravity. But at some point, if I experience 2, 3, 4 Gs outwards, then I'm not even going to notice the 1 G that actually acts downward. Right? Does that make sense? Yeah. Now, when you're spinning around like this pretty fast, experiencing maybe 3 Gs or so, I would guess probably about 3 Gs, you're experiencing this, and then all of a sudden they stop it, okay, or not instantly, but pretty quickly, right? They slow it down pretty quickly. I'm still actually experiencing gravity, but the trick of that ride is really neat. You perceive weightlessness. You feel like you're weightless, but that is completely an illusion. It's because your body has become accustomed for the last minute or so of experiencing like 3 Gs outwards, that all of a sudden when you're not experiencing that 3 Gs, you're only experiencing 1 G downward. You don't even notice that 1 G downward anymore. Does that make sense? Okay. Yeah, now in your car, don't try this. If you're going fast enough to experience, like, say, 3 Gs horizontally, like outwards like that, and you did it for like a minute, as opposed to like for 4 seconds, and you slow down pretty quick, then you would feel weightless. You would get that perception of weightlessness there too, even though you're not really weightless. It's just a trick, right?